Hi, everyone. My name is Xiaoyu Cheng. I graduated from Northwestern University and will be joining Florida State University as an assistant professor this fall. So first of all, let me apologize in advance that I'm still having symptoms of COVID. So we might hear some coughs. Hope that is not so distracting. For today, what I'm going to talk about is called the robust data-driven decisions and their model uncertainty. So when making data-driven decisions, the extrapolation from the sample data is often based on the observable similarities within a population. But in my settings, however, the decision maker also needs to take into account the possible and observed heterogeneity across individuals in the population. So for some examples, you can first of all think of online platforms such as Netflix and Google. And they often rely on the data from user feedback for making content recommendations. Well, they can categorize the users according to their online behaviors or online profiles. The user's preferences can also be determined by their offline activities that may not be observed by those online platforms. For another example, we can think of physicians often use the results from the clinical trials for making medication decisions. However, it is also well known that the effectiveness of the drug can also depend on underlying health or genetic conditions that may not be documented in those trials. So notice that in those settings, because the heterogeneity is unobserved, the decision maker might have a poor understanding or limited knowledge about not only how the individuals within the population might vary, but also how different individuals are going to be sampled from the population. So as a result, when using the sample data to make such a decision, the decision maker might be worried about the possibility that the sample data may be more from one type of individuals, whereas the future individual that determines the payoff of the decision may be more of a different type. So what I'm going to do in this paper is that I'm going to address this concern by using some of the notions and methodologies from the deficiency literature. And specifically, what I'm going to do is that I'm going to develop a decision theoretical approach I'm going to develop a tractable method for using sample data to robustly improve decisions under such uncertainty. So that is, no matter how the sample data are going to be generated from a population of heterogeneous individuals, the decision maker can always use the data to make a better decision than without using the data. And importantly, I also make an observation in this paper is that some common inference methods, such as maximum likelihood or Bayesian updating, cannot achieve this goal in this environment. And in fact, they may almost surely lead to a strictly worse decision than simply ignoring the data. So I'm going to show you this example in a few slides, but for now, let me be a little bit more specific about the decision environment that I'm going to study in this paper. So the concern in making data-driven decisions that I motivated in the previous slide is more precisely the possibility that the sample data and the future uncertainty can be governed by potentially different probability distributions. So therefore, to capture this concern in this paper, I consider a much general environment where the uncertainty is governed by a sequence of independent but possibly non-identical distributions. So I'm going to further call this sequence of distributions the DGP, or data generating process, or DGP, in the sense that the decision maker will observe the sample data given by the realizations of the marginal distributions of the DGP. And then she can make a decision whose payoff depends only on the future realizations of the same DGP. So notice that because the DGP could be a sequence of non-identical distributions, which captures the possible heterogeneity across individuals, it is indeed the case that the sample data and the future uncertainty can be governed by completely different probability distributions. So in addition, because the heterogeneity is unobserved, the decision maker may also face model uncertainty in the sense that it is uncertain about which model, or the DGP here, that governs the underlying uncertainty. So in this paper, I'm going to further suppose that the decision maker might only know there's a set of the possible DGPs that can potentially govern the underlying uncertainty. But however, she may not be able to further form any probability statistical beliefs over those DGPs in this set. So in other words, the model uncertainty here is going to be represented by the ambiguity over a set of the possible DGPs. And for decisions under ambiguity, motivated by making a robust decision, I'm going to further consider a case that the decision maker will apply the max-min expected utility criterion to making this decision. In other words, the decision maker will make decision that is optimal according to the expected utility under the worst possible DGP. So specifically in the presence of sample data, the decision maker can always choose to ignore the data and make a data-free decision based only on her initial knowledge about the underlying uncertainty. So that is, she can always make a max-min decision with respect to the initial set of the DGPs that she initially contemplates. On the other hand, given the sample data, the decision maker can also use the data to make some inferences about the underlying uncertainty so that she may update her initial set to a different set of the DGPs. And I'm going to formally define the data-driven decision as the max-min decision with respect to this new updated set of the DGPs. So given these two types of decisions, the formal question that I'm going to study in this paper is that how to make such inferences or how to update the initial set to this updated set of the DGPs based on the available sample data so that the data-driven decisions are going to be better than the data-free decision under the true DGP, the generated data. So it is important to notice that while the decision maker is making these decisions according to the max-min heuristic, because she doesn't know which one is the true DGP, but however, the performance of the decisions are going to be evaluated against the ground truth. So in other words, whether or not the data-driven decision is going to be better, is going to be evaluated and according to the true DGP that really governs the future uncertainty. So for today, I want to use a very stylized example to give you a little bit more sense of this question and also show you what is the intuition of the main result in this paper. So this example, so the purpose of the example is to, first of all, give you a concrete sense of the decision environment that I studied in this paper. But more importantly, I want to show you how maximum likelihood updating, which is the common inference method that I refer to, can almost surely lead to a worse decision in this environment, and also how to address such a problem by using the updating rule that I proposed in this paper. The example is given in the context of an online platform. Say Netflix is trying to use the sample data to make content recommendations. So specifically, suppose that Netflix might have the option to recommend either a standard movie or a personalized movie to some of the users. And given each one of the movie, the users might like it or dislike it. This gives Netflix a payoff of 1 or 0. And imagine that Netflix identifies a group of the users all have similar online behaviors and online profiles, but is uncertain about the outcomes of recommending either one of the two movies to those users. So specifically, suppose that there's a population of users and the uncertainty that Netflix is facing is given by the uncertainty over the safe space, given by the infinite product of all the possible outcomes from each one of those users. Those are the like and dislike from each one of the users. And more specifically, I'm going to assume that there's going to be no model uncertainty or ambiguity associated with recommending the standard content. So it is known that when recommending a standard movie, the users are going to like it with the same probability of 1/2 across all the users. So in other words, the DGP that governs the uncertainty here is given by the ID distribution with the marginal probability equals 1/2. And on the other hand, I'm going to also suppose that there's model uncertainty or ambiguity with when recommending the personalized movie. And moreover, Netflix knows that there might be two different possibilities. So the first possibility is that this movie might be a good match with the users, so that it is known that when recommending the personalized movie, the users are going to like it with the probability of at least 0.6, strictly higher than recommending the standard movie. But however, due to the unobserved heterogeneity across the users, the actual probability of observing a like from each one of the users is different, and it could be any real number between 0.6 and 1. So to capture this kind of uncertainty that we're facing in these possibilities, so the set of the DGPs that governs the uncertainty here is going to be given by this set, denoted by the interval 0.6 to 1 to the power of infinity. So which is the set of all the independent, but possibly non-identical distributions, where the marginal probability of observing a like is always between 0.6 and 1. So specifically, given an example here is that one candidate here is where P1 equals 2.6 and P2 equals 0.7 and P3 equals 1, and so on and so forth. So for the other possibility, the personalized movie might be a mismatch, meaning that it is less likely to induce the user to like it compared with recommending a standard movie. And in this case, only for simplicity, I'm going to further assume that it is going to induce the user to like it with the same probability of 1/3 across the users. That is given by, so that here the DGP here is given by the ID distribution with the model probability equals 1/3. So taking both possibilities into account, the set of the DGPs that represents the model uncertainty here when recommending the personalized content is simply given by the union of the two sets of the DGPs here. And notice that for recommending the personalized movie, the worst case scenario is that it is a mismatch with the users, so that it will give the Netflix a payoff of 1/3 across all the users. So therefore, only given this initial knowledge and without any further information, the date-free decision or the max-min decision that Netflix is going to take is going to recommend a standard movie to all the users. So next, let's see what happens when Netflix can also have access to the sample data from, for example, having recommended the personalized movie to some of the users. Moreover, suppose that given the sample data, the Netflix might use the maximum likelihood updating, which is formally meaning that Netflix will retain the DGPs that maximize the likelihood of observing the data. So in other words, given the sample data, Netflix, by applying the maximum likelihood updating, we would only believe that only those DGPs that are most likely to generate the data are still plausible to govern the future uncertainty. And for this example, I'm going to further consider the case that suppose the true DGP is indeed a case where the movie is a mismatch. In other words, it is governed by the ID distribution with a marginal equals 1/3. And then almost surely, in that case, Netflix will eventually observe some sample data with an empirical frequency of like close to 1/3. So however, the observation here is that the likelihood of such data is not going to be maximized by the true DGP among all the possible DGPs in this example. So how is that possible? So let's looking at the simplest case where Netflix observed 3 data points. So that is 1 like and 2 dislikes from the users. And the likelihood of observing this data under the true DGP is going to be given by 1/3 times 2/3 times 2/3. So next, let's also look at the likelihood of observing this data under the other DGPs from the other possibilities. And notice that because the set contains all the independent but non-identical distributions, the likelihood of observing this data can be maximized by assigning different marginal probabilities to different realizations of the data. So specifically here, the likelihood is maximized by assigning the highest probability of observing a like, which is 1, to the first user who actually liked the movie, and assigns the lowest probability of observing a like, which is 0.6, to the second and third user who actually disliked the movie. And in this case, the likelihood of observing this data is going to be given by 1 times 0.4 times 0.4. But however, notice that we have the following inequality, which implies that the likelihood of observing the data is in fact maximized by the wrong DGP, that is not the true one. And in fact, because this is a strict inequality, in the end, almost surely Netflix is going to observe some sample data with an empirical frequency close to 1/3. And for almost every such sample pass, there would always exist a DGP from the other possibility such that maximize the likelihood of the sample data. So in other words, by applying the maximum likelihood updating, Netflix will eventually almost surely rule out the true DGP from the set of DGPs that are still believed to be plausible. So let's see the implications for decisions of ruling out the true DGP here. So notice that the possibility of being a mismatch is the only reason for choosing the personalized substandard movie over the personalized movie. But however, when the possibility of being a mismatch is ruled out by using the maximum likelihood updating, the data-driven decision there is going to be almost surely to recommend the personalized movie. And then notice that, however, the future users, the responses of the future users are still going to be governed by the true DGP. So therefore, which gives Netflix the payoff of 1/3 across all the future users by taking the data-driven decision. On the other hand, notice that if Netflix simply ignores data and takes the data-free decision, would guarantee itself a payoff of 1/2 across all the users. So in other words, it shows that in this example, by applying the maximum likelihood updating, Netflix, by using the sample data, will eventually make a strictly worse decision than simply ignoring data. So a similar observation also holds when Netflix applies Bayesian updating in this environment. So let me use I guess I have a few more minutes. Let me use the final minutes to tell you what is the solution that I propose in this paper. So what in this paper I propose is called a new updating rule called average update. So the idea that is quite simple. It's going to ignore the patterns of the sample data, but only looking at the empirical frequency of the sample data. Specifically, it's going to retain DGPs whose average of the marginals of the distribution over the sample is close enough to the empirical distribution. So for example, if Netflix observes sample data with an empirical frequency equals 0.8, then by applying the average and update rule, Netflix will retain, for example, the ID distribution with a marginal equals 0.8, or the non-identical distribution whose marginal is either 0.6 and 1, but as long as the average is close to 0.8, then it's going to be retained, and many others, as you can imagine. So the key intuition of why this updating rule might work is that under any independent but possibly non-identical distributions, the empirical distribution converges to this average almost surely. So therefore, it ensures that by applying this updating rule, one can almost surely retain the true DGP in this environment that generates the data. So let's further see the implications for decisions. So first of all, when the true DGP is 1/3 to the power infinity, and then because the true DGP is not going to be excluded from the updated set, so the data-driven decisions are still going to be recommending a standard movie, so which gives Netflix the same payoff as taking the state-free decision. On the other hand, if the true DGP belongs to the other possibility, and then with sufficient amount of data, the driven decision is going to be recommending the personalized movie because the possibility of being a mismatch is going to be ruled out. And in this case, notice that because the responses of the future users are still going to be governed by some DGP in this set, so therefore the payoff from the data-driven decision are going to be at least 0.6 across all the users, which is strictly higher than the data-free decision. In other words, in summary, in this example, what I've shown is that by taking the average and updated rule that I proposed in this environment, Netflix with sufficient amount of data, Netflix can guarantee a data-driven decision that is either the same or strictly better than its data-free decisions. And what I do in this paper is that I further take this intuition to the general model and show that show that when and how these intuitions can be generalized in the more general environment. So not only for a single decision problem, but for example, for a sufficiently large family of decision problems. So I don't think I have time to go through the details here. And finally, let me show you the related literature to my papers. As I mentioned, this paper combines the methodologies from two literatures in decision theory. One is statistical decisions, the other one is decisions and ambiguity. And finally, thank you so much for coming to the talk. Thank you.
I think we have time for one question while Amy will set up the slides. Any questions? So I have one. Okay. So you showed a heuristic that is better than log likelihood and better than Bayesian. But do you know to say something about what is indeed the min-max optimal one? What is the one that maximizes the min-max payoff?
So in this paper, I'm not looking at the optimal notion, but I'm looking at whether the data-driven decision is better than the data-free decisions. So I'm only going to compare whether using some inference method or some updating rule, your decisions can be improved in a robust sense. So I agree that this may not be optimal in the sense that you might have different notions of optimality conditions, and you have some of them. So for example, there might be two rules can both improve the decisions, and one is better in some scenarios, the other one is better in other scenarios. So I haven't come up with a really optimality notion here, and I think that would be the next step of this case.
Okay, thank you.
Thank you for the question.